Those who are online are able to hear me. Yes, sir.
Yes, sir.
Are you able to see the screen?
Yes, sir.
Yeah, what was the last concept we discussed? Purila. Resistors in series. So shall we proceed? Next. So next concept that we'll see is resistors in parallel. Right. So those who are online are able to hear me?
Yes, sir.
Okay. Okay, listen to this. So when can we say that the given resistors are connected in parallel? First thing that should happen is potential difference across each resistor is a constant. Second, current supplied by the battery will get split across each resistor such that sum of individual currents, right? Sum of individual currents will be equal to the total current supply, right? So sum of the individual currents will be equal to the total current that is supplied. Here with this. So what will happen is, listen. If I take the resistors like R1, R2, and R3. Listen to this carefully, okay? I'm going to tell you something important. Listen. See, the logic I'm going to tell you now is the one which you're going to use to solve problems also. So listen to this carefully. So this V is the potential difference across the battery. I repeat it, it is a potential difference. Meaning of it is, when you take a battery, you know that it has a positive and a negative terminal. So positive terminal has a potential, negative terminal also has a potential. The difference between them is what is this. So when this is the scenario, if I take the potential of this point, each point can have a potential associated with it. So if I take the potential of this point as V, then the potential of other point can be considered to be 0. See, it is not necessary that this has to be V, this has to be 0. Okay. What I'm doing is, just to make things simple, one of the ends I'm considering it to be at 0 potential. Obviously, we'll take it for the lower end. You can take it as V1 and V2 also. Then what should be the condition? V1 minus V2 should have been V. Are you able to understand? That is first point. Second is, whenever there are 2 points which are connected only with a wire in between them, if there is no passive element existing, when I say passive element, I'm talking about the elements which take energy, like resistors, capacitors, inductors, right? When there is no element existing between 2 points and they are connected only with the help of a wire, both the points are said to be at the same potential. Meaning, this point and this point are at the same potential. Similarly, this point and this point are at the same potential. Are you able to understand this point? If that is the case, I want you all to think and tell me what will be the potential of this point. It will be V, and the potential of this point will be 0. This point is V. Makes sense? So what did I say in the first point? Potential difference across each resistor is a constant. So across the first resistor, what is the potential difference? V. Second, third also it is V. So that's what happens when you connect the resistors in parallel. Okay. Second is, when you take the current supplied by the battery as I, right? At this junction, the current, let's say it is getting split as I1. At the second junction, let's say it is getting split as I2, and at the third junction, I3. Then mathematically, what I can say according to the statement is, the total current supplied by the battery is equal to the sum of the individual currents across the resistors. Am I clear with this? I is equal to I1 plus I2 plus I3. Okay. Now the question is, how do I relate the potential difference across the resistor R1 to its current and resistance? So can I say that V across the first resistor, so the potential drop across the first resistor, can I write it as I1 into R1 according to Ohm's law? Then what will be the value of I1? V by R1. Similarly, what will be the value of I2? It will be V by R2. And what will be the value of I3? It will be V by R3. Take all these values and substitute it. So it will be V divided by R1 plus V divided by R2 plus V divided by R3. That is for the right hand side. But for the left hand side, what should happen? I need to draw an equivalent circuit for it. Equivalent circuit in the sense, I will replace all these resistors with one resistor whose value will be Rp, and the potential drop will be V. And if I take the current here as I, then what will be the relation between these three parameters? I will be equal to V divided by Rp. So can I write it as V divided by Rp? Everywhere I applied Ohm's law. So V will get cancelled, and what is that you're left out with? 1 divided by Rp will be equal to 1 by R1 plus 1 by R2 plus 1 by R3. So this is going to be the equation for equivalent resistance and individual resistances. Is that point clear? So please make a note of it. Should I proceed? So write down the next heading as 1 minute. So write down the next heading as electromotive force, which is also called as EMF. So next heading is going to be electromotive force or EMF. So listen to this carefully. See, I have 3 different batteries in my hand, right? So when you go to a shop and buy these products, right? When you buy these batteries, you will be able to see a specification given on top of it. So that specification is going to be the potential drop they would have given across the positive and the negative terminal. For example, for this battery, it is given as 1.5 volt. This is known as a AA battery. For this also, it is given as 1.5 volt. Okay. Whereas for this one, it is given as 9 volt. Right. This is the value which was mentioned by the manufacturer. Right. There's a value which is mentioned by the manufacturer. So what should happen if I give you a voltmeter? You take a voltmeter, place it across the positive and the negative terminal of this battery. What should the voltmeter show? It should show you 9 volt, but it will not show you 9 volt. Okay. There will be a slight decrease in the value. So why that is happening, I'll explain it to you. So this 9 volt, which is given to you, is actually the potential drop across this battery in open condition. So what do you mean by open condition? When this is not connected across any circuit, or to put it even more simple, when no current is drawn out of it. If you have not drawn any current out of it, its potential difference between the electrodes is going to be 9 volt. Whereas when you connect a voltmeter, you're actually completing a circuit, and remember that voltmeter has some resistance. So due to some drop, what will happen is you will not be able to measure the exact value as 9 volt. Okay. So why I'm telling this point is, when I say electromotive force, one of the misguiding factors here is we think that electromotive force is a force, but actually it is not force. It is the potential difference across a cell. So it is the potential difference across, when I say across a cell, across the terminals of the cell, right? Across a cell, most importantly in open condition. So to connect the dots, this 9 volt that they have mentioned here, what is this actually? This is what is EMF. That is why EMF and potential difference will have the same voltage, same unit, because they both are potential difference. Right. Now the question is, how exactly a cell is going to look like? If you observe, if I take a cell basically consists of a liquid inside it. Right. So it is going to consist of a liquid, and that liquid is called as electrolyte, which can basically split into ions. Let's say the electrolyte that is used here is NaCl for understanding. Okay. So a cell basically consists of a positive terminal and a negative terminal. I hope you are able to understand this point. So the positive terminal is called as the anode, and the negative is called as the cathode. Right. So when electrolysis happens, can I say that this will get split as Na plus and Cl minus? When it is getting split, what will happen to the Cl minus ion according to electrostatics? The Cl minus ions will be pulled towards the anode, and Na plus will be pulled towards the cathode. Right. So Cl minus, they have to move this side, and Na plus, they have to move to the right side. If that is the case, this Na plus and Cl minus ions both are moving inside a medium. Right. So they are moving inside a liquid medium. So in that liquid medium, what will happen is these ions will experience some resistance. Right. So the resistance which is offered by the electrolyte to the flow of the ions in itself is what is called as internal resistance. Are you able to understand this point? So internal resistance is represented by the symbol small r, and external ones are always represented with capital R. So in reality, what happens is every cell that you buy, cell or a battery, whatever you buy is going to have some internal resistance present in it by default. So theoretically, what we do is we consider all the cells to be ideal. In the sense, we take the small r to be 0. That is why we never spoke about where we are speaking about potential difference or electromotive force. But now I'll tell you how those two are actually related. When will electromotive force actually be equal to the potential difference in the closed condition? I'm going to explain it. Is it clear till this step? Are you able to understand the story? Right. So this is what happens. Now, whenever you take this battery and complete a circuit, then you take a voltmeter and measure the potential difference across this, right? What did I say? It will decrease, right? So how it is going to decrease is the potential difference across the cell when current is drawn out of it. Why I'm mentioning this point is there a way where you can give current to battery, where you can supply energy to battery? Other scenarios like that? No. Then how is your cell phone working? You connect it, you charge it. No, there is a possibility. You can charge a battery, rechargeable batteries do that. No? Whenever it gets drained, again it needs to get charged. There is a possibility of charging a battery or discharging a battery. Meaning, when I connect this phone across this circuit, I'm charging it. As soon as I remove, I'm discharging it. Means I'm trying to draw the energy out of the internal battery that is available. Am I clear with what I'm explaining? So listen to this carefully. Why is test on this point is the equation that I'm going to give you now is applicable when the battery is getting discharged, not when the battery is getting charged. So the potential drop across the terminals of a cell will be equal to E, which is the EMF, minus the current that is flowing through the cell itself into the internal resistance of it. Don't worry about it. I'll tell you how it has come after I explain certain laws. Okay, as of now, accept this equation. What is happening? The potential difference across the terminals of the cell is equal to EMF of the cell. That is, for this battery, it is 9 volt. You put 9 here, minus, you know what is the current that is flowing through that? Take that current and multiply with the internal resistance that this is going to offer. Are you able to understand how you are supposed to apply? That value is what the voltmeter is actually showing. I'll do it one day and show. Okay, you'll be able to see that there will definitely be a decrease. How much it is going to decrease depends on the condition of the battery. If it is a very new one, maybe the decrease will be very less. But you have used it much, it might fall to a drastic value also. Because at some point it has to die. The liquid has to get over, it has to die, no other option. Are you able to understand? So, having said this, listen to this carefully. If this is the scenario, when I'm saying that the potential drop is equal to EMF minus IR, it clearly indicates that the potential difference across the terminals of the cell is always less than the EMF, provided the cell is getting discharged. I'm stressing on this point. When it is getting discharged, when current is drawn out of the cell. Okay. Now the question is, till now, whatever problems we did, I never mentioned which is EMF or which is potential difference. Why I didn't do it is because we considered an ideal battery or an ideal cell, for instance. Okay. When we consider ideal battery, R value is internal resistance is ignored. When you take and put it here, what will happen to the mathematical expression? That is why we directly used it. Are you able to understand what I'm saying? So V will be equal to E. This is what happens with an ideal battery, and that is what we did in the problems that were given to us. Whereas, if I have to connect this dot, I told potential difference across the cell in open condition. What do you mean by open condition? When no current is drawn out of it. When current is not drawn, I'm trying to consider it to be a real battery. Means I'm saying internal resistance is not zero, but it is in open condition. Then what should I substitute zero? If I substitute for open condition, that is, if I substitute I is equal to 0 in this expression, whereas R is not equal to 0. When I do that, I'll get V is equal to E. Is this not the statement that I gave you? EMF is the potential difference across the terminals of the cell in open condition. You're able to connect the dots? So these two scenarios is when they both are equal. Otherwise, the potential drop is always lesser than the EMF, provided the cell is getting discharged. In most of the scenarios, it will get discharged. Right? So this is all about the EMF concept. So please make a note of it. புரியுதா? Those who are online, are you able to understand?
Yes, sir.
Yes, sir.
Good. The doubt, or? Shall I proceed? Okay. So the next concept that we need to understand, it's a very, very important concept. The next one which we are going to see are called as Kirchhoff's laws. So there are two laws. Okay. One is called as Kirchhoff's current law, which can also be called as junction or node rule. Okay. This you already know. You have already applied it. But only thing is you're now going to learn in the name of a law. That's it. In today's class, we saw. Okay. So I'll take a very simple circuit. Try to understand. Let's say there is a circuit which consists of two resistors R1 and R2, which are connected in parallel. Okay. Let's say the battery is supplying a current I. So what should happen? When can the circuit be complete? When this I goes from the away from the positive terminal, completes a circuit and comes back to the negative terminal, again it should start moving in a loop. Only then you can say that the circuit is closed. When the circuit is, so here I'm not going to talk about closed or open, but I know that the current supplied by the battery is I. So this I is going to reach this junction. You know what is a junction, right? It is a point which is connecting two wires. So at the junction, what is going to happen is you have two devices which are ready to draw the current. They are passive elements. What do you mean by passive elements? The ones which are drawing the current. The opposite of it is active elements, the ones which can supply energy. Okay, so resistors are passive elements. You come here at the junction, what will happen? Here the current is getting split. Let's say it is I1. I1 is a current it is trying to draw from which one? From the total current I. It is not supplying any extra current. I is the total current that the battery could give. Right? I1 it is taking. So what will be the remaining current that is going to flow here? Let me call it as I2. So basically, how is this I2 going to be related is what we are going to see. Based on that only, we are going to give a statement to it. Right? Why this current law is also called a junction or node rule is because this law is applied only at junctions. Okay. So look at the statement for it. I'll give you two statements. Look at them very carefully. Okay. Total current. When I say total current, sum of all the currents entering the junction. Total currents entering the junction is equal to the total current leaving the junction. Meaning, if I look at the junction, the total current entering the junction means the arrow marks which are towards it. How many currents are there? It is only one. I is equal to how many currents are leaving the junction, which are going away from the junction. They are I1 and I2. I need to do the sum of them. It is going to be I1 plus I2. So I told you we have applied this already. This is what is Kirchhoff's current law. Okay. So is this point clear? Right. This is one way of looking at it. The counterpart is if I put an OR case to this. Now what I can do is, can I write this I is equal to I1 plus I2 as I minus of I1 plus I2 is equal to 0. See, some books give the statement in this way. Let's see the other one also. It is like algebraic sum of currents at a junction is 0. Makes sense? What do I mean by algebraic sum? A scalar quantity dealt with sign. I didn't use vector sum here because current is a scalar quantity. So that is the reason why I use the word algebraic sum of currents at a junction is 0. Means to that scalar quantity, you give a sign. So how is the sign decided? It is up to you. In this scenario, I took capital I to be positive, meaning if I took the current entering the junction as positive, then the current leaving the junction will be considered as negative. That is what is written here. Observe, it is I minus I1 minus I2. So currents that were leaving the junction are considered to be negative, and the currents that were entering the junction is considered to be positive. So be very careful when you're stating, don't combine both and write it. Don't say that the algebraic sum of currents entering the junction is equal to algebraic sum of current leaving the junction. No. Whenever you use the word algebraic sum, you're equating it to 0. If you're just using the word total, you are equating the currents on both the sides. So look at the small difference. Here I use the word total, here I use the word sum, but there is a prefix. It is algebraic. Am I clear with this point? Right? So please make a note of this. Can I proceed? Listen. Now the question is, since I'm saying the currents entering is equal to the sum of the currents that are leaving the junction. Okay. Now, on what principle does this law work? So, this law specifically works on the principle of conservation of charge. Because we are speaking about current. So, Kirchhoff's current law or junction rule or node rule works on the principle of conservation of charge. Is that point clear? So this can be one such question that can be asked in your MCQs or assertion reason based. At that point, you should know this. Am I clear with this? So make a note of it. Shall I proceed? Yes. So the next concept that we are supposed to know is Kirchhoff's voltage law, which can also be called as KVL. So in the previous case, you can also call it as KCL because it is Kirchhoff's current law, no? So KCL is current law, KVL is voltage law. So the difference is when you want to speak about KCL, all that you need is a junction, right? Whereas when you have to speak about KVL, all that you need is a loop. That is why sometimes this is also referred to as loop rule. Okay. So before I explain what is Kirchhoff's voltage law, let me explain where Ohm's law comes and what is the drawback of it. Okay. So listen. One minute. I'll take a very simple circuit. So when I draw something like this with smaller inside a box, it is understood that you're talking about a cell with some internal resistance. Okay. So all that I'm interested is, it's a very simple problem. All that I'm interested is to calculate the amount of current that is flowing through the circuit. Right? So there is only one cell. Let's say the current supplied by the cell is capital I. Right? So here, can I say that E is equal to I into, observe, I am applying Ohm's law only. One battery, but I have two resistors. So what I'll do is I'll replace those two resistors with one. How? By considering them to be in series. Right? So can I say that E is equal to I into capital R plus small r? So what will be the value of I? E divided by capital R plus small r. Am I right? So how I derive this value is using Ohm's law. Now what I'll do is, we need to understand one thing. See, this is a simple problem. We could solve it using Ohm's law. But what if there is a scenario where you have more than one cell present? And if you're not able to break it down to a simple circuit of this format, right, that is when you will get stuck. And that is when KVL will actually save us. Right? That is why this law is existing. Whenever a circuit becomes complicated with more number of batteries, right, and more number of resistors, which cannot be simplified into a smaller one. Clear? So the statement is like this. Again, it starts with the word algebraic. Algebraic sum of, I repeat, algebraic sum of the potential drop across each element in the circuit is 0. So what I'm doing here is, again, I'm taking the algebraic sum into consideration. But this time, the algebraic sum is taken for which physical quantity? It is for the potential drop. So you take the algebraic sum of the potential drop across each device present in the, sorry, I need to correct this, each device. Each device present in the loop. Each device present in the loop is 0. I repeat, the previous case, when we talk about Kirchhoff's current law, we take the algebraic sum of currents, whereas in this scenario, we take the algebraic sum of the potential drops across each element. When I say each element, they can either be active element or passive element. Active elements are cells, right? And passive elements are the ones which are drawing energy from them, right? Now, I'll tell you how to, whenever you see algebraic, no, all that you need to know is sign convention. So I'll tell you how to understand the sign convention first. then I'll frame the equation and try to calculate the value of current using KVL, that is the Kirchhoff's voltage law. Observe. First thing that we need to have in our mind is, when you take any loop, if I take this loop to be ABCD, which is a simple loop, right? So if I consider the loop to be ABCDA, always whenever you're mentioning a loop, start and end point should be the same. Okay. The question is, current can flow only in one direction. In this case, the current can flow only in one direction. Am I right? What direction is this? In this example, it is flowing in the clockwise direction. But we can go across the loop in any direction we want. Meaning, what I'm trying to say here is, I consider the loop to be ABCDA, which is exactly matching with the direction of the current. But not necessary that you should always take the loop like this. What is the meaning of a loop? Starting and ending point is same. So I could have taken the loop as ADCBA also. It is still a loop. So what I'm trying to say is, you can take the loop like this or like this. This is our freedom. But you need to have clarity with one thing. In whichever direction you are taking the loop, that is the direction in which you are walking. So that is the direction in which you are walking. Okay. So first, what we need to do is, across each element, we'll put 2 points and understand which point is at higher potential and which one is at lower potential. So the higher ones, I'll represent it with capital H, lower with small capital L. So who will tell me which is at higher potential or lower potential? It is the current's direction, because current always flows from higher to lower. So if you observe in this case, current is flowing from A to B. So A is considered to be higher. This side is considered to be lower. So first step is mark like this with a pencil. Right. When you go from B to C, there is nothing. When you go from C to D, you're encountering two elements, one resistor and a cell. Okay, battery. So if I take 2 points here, across this internal resistor, what is happening? Which side is higher? C is higher because the current is flowing in this direction. C is higher and this point is lower. Similarly, across the cell, it is fixed. There is nothing you can change. Smaller line is lower, bigger line is higher. Okay. So, listen. Whatever direction you take the loop to be, if at all you are walking from higher to low across a device, you consider the potential difference across that point to be negative. Whereas, if you walk from lower to higher, you consider it to be positive. See, there are two ways to understand this, okay? I am telling with the help of higher and lower. Some books refer to it as direction of current. Both are same. But the logic is simple, okay? If at all you read it in the reverse, it is still correct. Reason being, when you write it as algebraic sum, right-hand side is what? Right-hand side is a 0. So whether you write minus x plus y or x minus y, both are same. So I'm just telling my method. So in my way, what I'll do is, first I'll take the higher and the lower ends. Then I'll try to understand. See, this will come with practice. Maybe first 10 to 15 problems you need to apply this. After that, you need not mark it. You will be able to write it on your own. Okay. So I'm saying higher to lower is considered to be negative. Negative of what? Negative potential drop. Lower to higher is positive potential drop. Why I'm taking it as negative is simple. If I take an object and drop it from here, if I take the ground to be the reference, this is at higher potential. When the object is traveling down, it is losing its energy. That is why minus. Same logic. Okay. So observe, what I'll do is, if I go from A to B, when I'm going from A to B, how many devices do I have? One. So across the device, when I go from A to B, am I walking from lower to higher or higher to lower? Now forget about direction of current. You have nothing to do about direction of current. Okay. You higher to lower, I should take minus. So negative of what is the potential drop across this resistor? It is capital I into capital R. This is according to Ohm's law, no? V is equal to IR. From B to C, there is no device. So leave it. So when you go from B to C, there is no device, leave it. When you go from C to D, you're overcoming two devices. Right? What is happening there? Across the internal resistor, when you move from C to D, you're moving from higher to lower. Again, negative of how much? I into. Whereas when you walk across the battery, it is plus E because across the battery you're walking from lower to higher. So when you walk from lower to higher, you just write the EMF. To put it simple, what I'm trying to tell you is whenever you have resistor, you need to write the potential drop in terms of I and R using Ohm's law. Whenever you have a battery, just write that value there. That's enough. So how many devices are there in the circuit? 3 and 3 terms. So only hint is when you write the expression, there should at least be one term which is having the opposite sign of others. For example, here you have minus minus, at least one should have a plus. Reason is very simple because when you add everything, the answer should come out to be 0. If everything is negative, sum of all negatives can't be 0. Similarly, sum of all positives can't be 0. That is why you need to have a mix of opposite signs. Okay. So this should be equal to 0. What I'll do is E is equal to I into capital R plus R, which implies I will be equal to E divided by R plus R. So that's what happens here. You're able to understand whether you're going to use Kirchhoff's voltage law or Ohm's law, you're going to get the same answer. But when will you need this? I repeat it. When will you need Kirchhoff's voltage law? When the circuit is getting complicated, where you're not able to break it down into a simple, it's not like a mixed circuit. You're not able to break it down into a simpler circuit and convert it into one battery and one resistor, where you're failing to apply Ohm's law. That is when you need to use this. Am I clear with this? Why are we taking? A and B also, there is no wire, no? I mean, there is no device, no? Iruka. And then logic, see, mathematically, the logic is simple, Ra. Whenever you apply this voltage rule, number of elements should be the number of terms. How elements irukka? Capital R, small r, E. 3. How terms irukku? That's how it works. Okay. Are you clear? Those who are online, are you clear?
Yes, sir.
Yes, sir.
Yes, sir.
Good. So one last point to be mentioned here is Kirchhoff's voltage law works on the principle of conservation of energy. It works on the principle of conservation of energy. So Kirchhoff's current law works on the principle of conservation of charge, and here it works on the principle of conservation of energy. Clear with this? Yeah. What an extension. Clear? Okay. This is all for today. I'll tell you what I'm going to explain the next two classes. So I told you about cell today, right? So next class we'll be discussing about cells in series and parallel. Okay. And I'll be explaining about what happens when the cell is getting charged and discharged, and electrical power. And the last concept that is left out is Wheatstone bridge. So basically we saw Kirchhoff's law, right? So the application of Kirchhoff's law is Wheatstone bridge, and the application of Wheatstone bridge is something called as meter bridge. I'm not sure if while writing your record you could find something as meter bridge. So that is actually an application of Wheatstone bridge. Okay, but meter bridge, I think it is deleted from syllabus. If time permits, I'll teach you. Okay. So hopefully by Wednesday we should be done. Right? So revise and come. If there is any doubts, I'll see you guys. So those who are online, I hope it is clear now.
Thank you, sir.
Yeah.
Yes,
Thank
sir.
you, sir.
Thank you, sir.
Yeah.